It's already 6 p.m. I will wait for a couple of minutes. Let's see if people join, or otherwise, I will start the session after a couple of minutes. Okay, so let's wait for 2 to 3 minutes. I'm waiting so that people can join, otherwise, I will start. Okay, I think we can start. You can hear me properly, right? Anyone confirm? Okay, thank you. Okay, so let's start the session. Welcome to the live session for the course Sensors and Actuators, and this is week 3. Let me introduce myself first. I always start the session by giving an introduction about myself. So, I am Ananya. I am a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI. As of now, I'm not working in sensors. Earlier, I did work on sensors during my MTech project. Right now, like I do fabrication, like in our lab, we do fabrication of different semiconductor devices and other materials. So in this week, so we will mainly discuss about different fabrication processes. In the lecture videos also fabrication process of different sensors were discussed for this week, so we are going to discuss about those topics and solve few questions. The idea for this live sessions is that so in this course we don't have many numerical problems, but NPTEL live sessions are mainly focused to solve numerical questions or the types of questions those are normally given in the assignments or comes in exams. Okay, so I try to conduct this session in a way that I include the overview of the topics those were covered in the week, as well as few problems and few questions. Okay, so let's start it. again, I'm just letting you know that I'm recording the session, and I will be in the presentation mode for most of the time. So if you want to say something, you can unmute or you can write in the chat box. I will check in between. Okay. Or if you have any doubt, like I will take pauses in between, so then at that time also you can ask. So I hope that you have gone through the lecture videos for this week. So let's start with the topics those were covered in this week. So first topic was photolithography. Okay. So we briefly discussed about photolithography last week also, um, but in this week I think there was one lecture video on photolithography. So we will discuss about this now. So what is photolithography? I discussed earlier that when we want to fabricate a sensor or any device, we there are certain steps. Like what we do deposition. When we want a thin film of a material, then we also do lithography. That is a patterning technique. Okay. Patterning generally come like we do patterning plus etching together to get some pattern. I mean lithography and etching together to get some patterning. Okay. So that we can make different structures. And then another component in fabrication is doping, when we want to change the properties of our material, whatever we have deposited or whatever we are growing on top of a substrate. We are not discussing about doping here. About deposition we have already discussed in earlier sessions. So there are several deposition techniques. Some of them are like physical methods and some of them are chemical method. Physical method generally involves some kind of evaporation or sputtering, and in chemical methods some chemical reaction happens between either your substrate or the material, between the substrate and the material you are growing, or if there is already a layer, intermediate layer, and the material you want to deposit, some chemical reaction happens in like chemical deposition techniques. Okay, so we're not going to discuss about deposition techniques in today's session. We will mostly focus on patterning, that involves lithography as well as etching. Now lithography, like there can be different types of lithography also. We will discuss about photolithography because we are talking about sensors and actuators which are in micro dimensions. If our dimension is very small, then we cannot go for photolithography. We use different other techniques such as e-beam lithography, but for this course we will discuss about photolithography. Now in photolithography we use UV light source for patterning. Now the wavelength of the UV light source can be different. You can look into it. So UV source is ultraviolet, right, which will be below the visible frequency range. We know that visible is from 400 nanometer to 700 nanometer wavelength range, and so UV is below that. And why we can make micron dimensions devices using photolithography, and why not very small devices? It's like, see, this is the tip of the pen. Suppose you are writing something with this pen. Can you make a straight line which is thinner than the tip of this pen? This is something like that. So we cannot make very small devices which are like, say, few nanometer using photolithography, but for micron devices, photolithography is a very good technique already established. Mainly with, we know how we can do photolithography basically on silicon substrate. Everything is well established, so we often use this technique for fabrication of MEMS based sensors and other micro devices in micro dimensions. Okay. So there are several steps in a photolithography process, And so I do lithography in our lab. So I'll explain, I'll tell you that each and every step can be critical. If you do some mistake, like in any of the steps, your overall patterning, the final pattern you want, that will not be exactly same as you wanted. Okay, so the first step, so this diagram explains the lithography process. Now this diagram can be little bit different depending on what you are doing, what kind of photoresist you are using, and the properties of the photoresist can be different. But this is like a general representation of a photolithography process flow. Okay, so first step is what you do. So this is step 1. This involves substrate cleaning. Okay, now substrate, that can be a bare substrate, say a bare silicon substrate, but it can be a substrate with already some deposited film on it. Okay, maybe you are doing the lithography on a film, on top of a film. You say you have a substrate, and on top of it you have another thin film of your material, and you are doing lithography on this substrate plus thin film layer. So this can be done when you want to do selective etching of your deposited thin film, or you can directly do a lithography on the substrate, and then you can deposit and then do etching. There is another process that is known as lift off. I will discuss briefly also today. So whatever you have, like a bare substrate or a substrate with some thin film layer, or it can be a substrate with one layer of lithography, one layer of patterning is done, then you are doing the lithography on top of it, because to make devices we normally do multiple steps of lithography. On one pattern we do another pattern. uh, this can be anything. First, what you do, you clean your substrate. Now this cleaning can be different based on the substrate also. It can vary, like what is your, like how critical your dimensions are. Normally we start with like a basic solvent cleaning, which can be like a cleaning with acetone and IP and DI water. And if you are making a device with very small dimensions and you are going to do something like very critical measurement, then you go for other types of cleaning to ensure that there is no contamination. Okay, for silicon we know that RCA cleaning is also available, and piranha cleaning also you can do. It depends on your what you are going to use the device for. Okay, but it is always a good idea to start with a clean substrate. Next step is photoresist coating and baking. Okay, now how you do this, you do a spin coating of photoresist. Okay, so spin coater, it's a machine where you can set the RPM, speed of rotation of the substrate. And you what you do, normally you have the substrate, you uh, like drop like few drops of photoresist you place on the top of your substrate, and then the substrate will rotate at a certain speed. And now based on that speed you will get is, and the viscosity of your photoresist, you will get a thin layer of photoresist on top of your substrate. Now the photoresist, so this is the PR coating. Photoresist is, I will use this abbreviation PR. So it will have certain thickness, and that depends on the speed and the type of the photoresist, and it is usually written in the given in the data sheet of the photoresist. Okay, so you can see I have given this, I have taken the screenshot from a photoresist series. This is ARP 53 photoresist. Okay, this is I'm just giving you for your reference. So here in this data sheet, okay, is there any problem? Someone has written something on. Okay, there is no message. I don't know. There was some notification. I don't know what. Okay. In this data sheet you can see that there are two types of photoresist. The information for two types of photoresist is given: ARP 5320 and 5350. If you put some photoresist on your substrate and you rotate with this condition 6000 rpm for 60 seconds, then you will get a 4 micrometer thick photoresist layer on top of your substrate, and this is the information for 5350. Okay, now you can see that thickness is given like in micrometer, and it is very important in certain cases, especially if you want to do lift off. Lift off is a process where uh, which is which is used normally to do the lift off of metal to make some metal patterning. Okay, now once you get a certain thickness of photoresist on top of your substrate, you go for baking. In the class, the baking, on what condition we do this baking, like before exposure the baking is done. So white is done, so the photoresist contains some solvent, so you do this baking to evaporate this solvent, and so that you get like a good layer of photoresist on top of your substrate. Now the condition for this baking can be little bit different. There are like standard photoresist, those uses like maybe around 90 to 95 degree, but usually the range is between 90 to say 105 and 100 degrees Celsius. Don't get confused with the number, because this can be different depending on the photoresist. You follow whatever was mentioned in the lecture videos, that will be for some particular photoresist. Okay, for this ARP 5350 series, it is the condition is given as this is 105 degrees Celsius for 4 minutes at hot plate. And if you use a conventional oven, like many of you have in your lab maybe, so for in that case it will be 100 degrees Celsius for 40 minutes. Okay, next step is the third step. So this is not only UV exposure, this is UV exposure. So what you do in the third step is you load your mask into your system. You know what is a mask? Okay, some portion of the mask will be transparent and some portion of the mask will be opaque. uh, like how mask is made, that is a different like topic, but normally the mask is like a glass or quartz. On top of it chromium is deposited with certain certain areas will be dark, those areas will have chrome coating, and other area will be transparent to the glass. Okay, in step 3 you load the mask first to your photolithography system, and then what you do, you align your sample to the mask. Okay, so why this step is important? The step is important if you have multiple levels. Say this is the final pattern what you are getting, and you want to do some deposition on top of it. Say you have this kind of pattern already, and then you want to make another metal deposition, say here. on top of it. Okay, so in this case alignment is required so that your mask actually falls here, so that you finally not so if you don't do your alignment properly, instead of getting this kind of a design, what you will get, you will have something like this. If your sample is misaligned, you will get metal, say here, I don't know exactly what will be the pattern. Basically you will not get your desired features if you don't align your sample. Another reason why this alignment is required, because sometimes your sample may be like very small and your mask is very big, say. Okay, now there will be some features here in the mask. You want certain feature to be on top of your sample. Okay, sorry for the background noise. So you want some portion of your some features on the sample, right? So you need to do alignment, so you will move your sample little bit here and there, so that the features you want will be exactly on top of your substrate. Okay, on top of your sample. Okay, now after you align your sample, then you do UV exposure. UV exposure is done for certain duration. Okay, there will be certain intensity of your UV light source, and you will expose it for certain duration. Overall you will get the exposure dose, which will be in this unit, millijoule per centimeter square. Okay, now this is normally given in the data sheet, how much intensity, how much dose is required for a particular photoresist. So you will adjust your exposure duration based on this, and you already know the intensity of your light, so you will expose for certain duration, and if you multiply it, so that your intensity of your light will be in watt. So it will be in milliwatt per centimeter square, and if you multiply with time second, overall it will be millijoule per centimeter square. So you can do this calculation, you can do the dimensional analysis, how we get from the intensity to a required dose. Okay, after you do UV exposure, then you will unload your sample and unload your mask. Okay, this is also important, so that you don't when you do UV exposure, your mask and sample will be in contact. Usually you can do another type of exposure when your mask and sample are like little bit away from each other, but normally we make contact between the mask and the sample, and then we do exposure. That will give like better resolution or of like our features. Okay, otherwise what will happen, if there is a gap, light will leak through this area also, and overall your dimension will be different. So ideally what you want, whatever your dimensions are in the mask, you want similar dimensions in the photoresist pattern. That you will not get if the contact is not proper. Okay, now so after exposure, what you do, you like uh, remove your sample. So you don't want to break the mask or something, so that process is also like, you have to be bit careful while handling your sample. Okay, that you do. And after that, what for some photoresist this is required, not for all photoresist. So this is step 4, which is post baking. After the exposure, another baking is required for some photoresist. SO8 is one photoresist where we need post baking after the exposure, but for this photoresist 5350 series, it is not required. You can see that after exposure we can directly go for development. So it is a critical step for certain photoresist, may not be like, it can be optional for other photoresist also. Okay, now after the post bake, what you do, you do something called development. Okay, now what happens, due to UV exposure, the properties of the photoresist changes. If it is a positive photoresist, the areas where light is exposed, those will become soft. And in case of negative photoresist, the areas where light is exposed will become hard. Okay, so in case of positive photoresist, this is for positive photoresist. When we like dip your sample in the developer solution, so in these areas, for positive photoresist, these areas will be soft because light is incident here, so this will get like dissolve in the developer solution. Okay, if it is a negative photoresist, for this side you can see this portion will become hard, and that portion will remain and other portion will be developed. By developed, what I mean, in this portion will be dissolved in the developer solution. Now developer solution for every photoresist, certain developers are available. So you can see here the conditions are given for these photoresist 5320 and 5350, and how long you want you will do the development, that is also given. Okay, for 2 minutes or 60 seconds, it can be different for depending on the photoresist. Okay, uh, so you have to optimize this process, like exactly how what is the duration you want to do for development, what is the UV exposure time you want to keep, that those things you have to optimize for your case. Okay, now so these are the pattern you got after developing your photoresist. You can see here, using the same mask with different photoresist, positive and negative, we are able to get, we can get like a complementary kind of structure. Okay, so basically if you have in one mask, so this mask normally like the facility is not available, we normally made it somewhere. So depending on your resist, you can make like a different types of design. Okay, if you design a mask properly, then you can actually make it useful for like maybe two applications with different types of photoresist. Okay, now after development, the process is given here. So this is one kind of patterning, so patterning is already done. Now what you can do, ultimately you don't want photoresist, you want some material, say you want some metal deposition on top of your substrate. Okay, so what you do, say here you do like a metal thin film deposition here. Okay, so this film will be something like this. Okay, this is metal, this portion is metal. Now what you do, you do etching. So first you can see here, see that there is a layer of metal on top of the photoresist also. So what you do, you do polishing. This can be like a mechanical polishing, it can be a chemical polishing, it can be a combination of both, so that you remove the top metallic part of your top metallic part, and maybe little bit of photoresist also with polishing. Okay, next what you can do is you can do a process called etching. Etching is what? It is the selective removal of material. Okay, now you will remove your only your photoresist part, not the metal part, only the photoresist here, not the metal part. This will be like a typically a wet etching. We can easily remove most photoresist with acetone. I don't know whether like all photoresist can be removed it for acetone or not, but at least the one I'm working with easily gets removed with acetone. So say you remove your photoresist with acetone, you will finally get a pattern of metal layers like this. This is for positive photoresist and this is for negative photoresist. Okay, now this is one way to do one way to get a metal film or metal pattern on top of your substrate. There are other ways also, like I mentioned. So what you can do, you suppose you have a substrate and you already have a metallic film on top of it, then you can do lithography. Say this is your photoresist. Okay, this is your metal film and this is your substrate. Okay, Next, what you can do again is selective etching. Some chemical or some method, reactive ion method, that will remove only this metal part, not the photoresist. Okay, there will be certain chemical, and once you remove these photoresist, this metal part, so you will end up getting so this is very messy. You will end up getting some pattern like this. This is your metal, this is your metal, and photoresist layer will be on top of it. Then you can remove photoresist with some chemical, say acetone, and finally you will also get some pattern like this. So there are multiple ways to achieve like patterning. You can either deposit the film before doing the photolithography process, or sometimes you can do the deposition after the photolithography process as it was given here. It depends on your choice of material, what you want to deposit, and also depends on the facilities available. You can take any of the route. Okay. uh, yeah, so here you can see post bake is optional. After development also sometimes post bake required, and then you do customer specific technology, like you do these processes and then you remove photoresist. Okay, another method of removing photoresist is also oxygen plasma etching. Oxygen plasma treatment is very useful to make like basically this is used to clean substrate, and for better adhesion people use. For photoresist removal also this process can be used. I hope this photolithography process is clear. I hope that you have already watched the lecture videos, and from this explanation also it is clear. If you have any doubt you can ask. If there is no doubt, I will go to the next slide. So in this week, micro machining was also discussed. So we know that there are two types of micro machining technique. One is bulk micro machining, another is surface micro machining. So what is micro machining in like in this context? So it is removal of material. So in case of bulk micro machining, we remove a significant bulk portion of material. Say we have a substrate, we remove most of the portion of the substrate. Okay, that is why it is known as bulk micro machining. And in case of surface micro machining, we remove material from we do the micro machining on at the surface level. Okay, now why we need bulk micro machining and surface micro machining? We need these techniques to make MEMS devices. So you know that in MEMS, micro electromechanical systems, we have this micro channels, micro cavities, and cantilevers, like micro cantilevers. So to make this kind of structures, we need to etch or do micro machining of our substrate. Okay, now for bulk micro machining, basically it is like etching. So what we have these two techniques, isotropic etching and anisotropic etching. So what means isotropic etching? So etching in all direction is same. Etching rate, basically etching. Okay, in case of anisotropic etching, it is also known as directional etching. The etching rate is not same in all direction. Okay, So normally when we do etching with chemicals like wet etching, those are usually isotropic etching. And when we do dry etching with some physically hitting the material with some ion and then remove the material, those are known as ion beam etching. So those are usually directional or anisotropic in nature. Okay. Now usually chemical etching is faster. The etching rate is faster. You will be able to etch like a significant portion with a less amount of time compared to dry etching techniques. And also dry etching techniques are usually expensive because those need different types of instrumentation which are costly, uh, whereas chemical etching can be a little bit toxic and you have to handle the chemicals carefully, but it is usually you don't need like a very sophisticated instrument or environment to do this kind of etching. Okay. So but the disadvantage is that uh, these are isotropic. Here you can see that so the opening you have say of this dimension, this is the W, but after so you are, say you made a photoresist pattern with a opening of W, and you want to etch away of this window, from material from this window of this width, but because of isotropic etching you are getting this reason also. So overall your width will be W will be W plus some 2 delta W, don't know. So your pattern will be slightly different than what you actually want. So one way is to that you initially make a smaller window and then do etching, uh, but again it maybe it will not have like, you need to control your process very precisely so that you get the desired etching, even though it is fast. So you will not be able to like get a proper dimension as you actually wanted. So in that case dry etching is preferable if you are working with some critical dimensions, but you need a certain machine for that, and usually these are very slow. Okay. Now best of both of these two will be reactive ion etching or dry reactive ion etching, where you use both chemical etching and dry etching technique, combine both of this to get a an isotropic etching or directional etching with a much faster rate. Okay. This was discussed in the class, what is bulk micro machining. I'll not go into the details. If we uh, talk about, if we discuss about like fabrication of particular devices using bulk micro machining and surface micro machining, then in the later weeks also we can discuss. Another technique is surface micro machining. Here you make the structures on top of your substrate. So say you want to make a cantilever, you want to make a suspended beam, then in that case you use surface micro machining technique. So what we normally do in this technique is that you can see these steps A, B, C. First we make a sacrificial layer. uh, this layer we are going to remove it later. Okay, this is just to support the suspended structure we are going to make. Then we make then we deposit the material that we want, say some material which shows piezo resistivity, that shows some say we are making it for to make a suspended beam or cantilever kind of structure. So whatever material we are working with, we'll deposit it on top of the sacrificial layer, and then we will remove the sacrificial layer with some etching technique, so that finally we will get this kind of a suspended structure on top of your substrate, and we will be able to put force and pressure here, that say this membrane will band like this. Okay. So we will be able to do this such kind of will be able to design such kind of sensor, force and pressure sensor, using the surface micro machining technique. Okay, so these are very very important in case of MEMS fabrication. Okay, fabrication of MEMS based devices and microfluidic devices. Okay, another technique, another topic that was discussed in the class was wafer bonding. Okay, what is wafer bonding? Wafer bonding is basically, as the name suggests, it is the joining of two or more wafers together. uh, there are different types of bonding, that is direct bonding, anodic bonding and intermediate bonding. If you are interested, you can look more about it. I'll just give you what the names here. Direct bonding, another is anodic bonding. This is used in case of silicon, very frequently. And then intermediate layer bonding, where if the materials of your wafer and the two wafer does not make the bonding naturally, there no such reaction happens between the substrate, and you maybe do the bonding with an intermediate layer. Okay. The one example was given in the class for bonding was the PDMS micro channel with a silicon wafer or glass substrate. So this kind of bonding. So this is very important when we want to create say micro channels with some substrate on some substrate, and then we want to bond it with another substrate. Okay. Next topic that was discussed in the class was soft lithography. Soft lithography is a very popular technique because it is like a very cost effective technique. It is relatively easy, does not require much sophisticated instrument compared to photolithography, and usually reproduce many devices using the same mask. Okay, so this is the basic process flow of a soft lithography. So for the first step, you will have a mask. Okay, so uh, you will have this mask. This is called as master. Okay, this is usually made using photolithography process. Okay, so this is like a rigid substrate, and on top of it will be patterned. Okay, so in for this example, this figure I have taken from Google. So here you can see that this layer is SU8. Okay, so SU8 is a negative photoresist, and after the UV exposure, this SU8 becomes very hard. Okay, you will not be easily remove SU8. You need a particular agent for particular chemical to remove SU8. Okay, so this is usually very hard, very stable. Okay, not like other positive photoresist that gets removed very easily. Okay, so this is, say, normally this is done on top of a silicon substrate, and you make these patterns of SU8, or it can be of different material. But what I want to say that this is normally a rigid substrate and like a very stable material, or like a silicon pattern. This is a patterned you can say this is like a stamp. Okay, the stamp you use on paper. Okay, now what you do in case of soft lithography, you pour PDMS. So this is a polymer, so you can pour the PDMS like pre-polymer, and then you can do something called curing at certain temperature. That will be different depending on the polymer type, so I will not go into the details, and also I'm not very aware of what are the conditions those are necessary for PDMS curing. You can look if you are interested. So I will explain you the basic process. So what you do the curing of PDMS, and then you remove the PDMS layer using peel off. So it's just, this is your master stamp. You pour PDMS, you cure it, and then you peel normally from one side. I hope you can see me. Okay, normally you remove it from one side. Okay, and finally we'll have this PDMS stem, which is like the opposite of the master that you have. Okay, you can see here. Now this PDMS stamp, in the class what was given example was that this PDMS stamp can be directly used as a micro channel, right? This is your PDMS stamp. You can do a wafer bonding with another substrate, say glass substrate. And this will be your micro channel if this dimension is in micrometer. Okay, now this is one process flow of soft lithography. There are different types of soft lithography. I'm giving you some example for your reference here. So this is replica molding. So suppose you make a PDMS stamp, uh, and you can use it to like make another stamp, which will be again like opposite of the stamp, just like this one. Okay, using the same PDMS stamp. Okay, this is basically replicating like the structure on top of another, using another polymer. So that is why this replica molding, this is like a molding technique. Okay, this tech process is known as replica molding. Suppose you have this kind of structure, you can get another like opposite kind of structure using the similar technique. Okay, next one is micro contact printing. This was not discussed in the lecture series. I'm just giving you for a reference because soft lithography, like there are several types of soft lithography techniques. One was discussed in the class. So another type is micro contact printing. Suppose you make the PDMS stamp, and then so this is some material, this ink. So what you do, this is just like a stamp you use on paper, right? You have the stamp, you dip it in ink, and then you press it on top of the substrate, and you finally get the ink on top of your substrate, just like uh, placing or like using a stamp on paper. Okay, so this is also technique very popular, like people use it to make multiple devices. This will be like relatively, like this process will be very fast compared to do lithography. You have seen that. So this, using this technique also we are getting some pattern on top of our substrate. Okay, if you can make a ink of your material. Okay, then you can easily make this kind of structure on top of your substrate using a PDMS stem. This process will be much faster compared to a photolithography process. You have already seen that photolithography involves multiple steps. This will be much faster, and you can use the same PDMS stamp. You can clean this stamp, and then again dip it in ink, and then again do the printing very easily compared to like a multi-step photolithography process. So people use this for large scale fabrication, for of many devices or many pattern substrates. Okay, another technique is micro molding. You can see here. So on top of your substrate you place your PDMS stamp. You fill this with some pre-polymer that you can cure. Okay, and once you cure it with the condition that is necessary for this pre-polymer, you will get this polymer structure on top of your substrate, which will be kind of opposite to the PDMS stamp you start with. Okay, so these are different types of techniques. The advantage of soft lithography, as I mentioned, is this is relatively easy, low cost. However, there are certain trade-offs also. You cannot make very small samples, like very small dimensions with this lithography, and as well as you have to be very careful while you peel off the PDMS layer or PDMS stamp, because some of your structures will like topple or something. Say in this case, If you are not careful, you will end up your structures like this. If your like this um, height is very high, then they may topple on top of each other. Okay, so these are the like things that you have to be careful with soft lithography. But this is a very good technique to make microchannels and microfluidic devices. Okay, I hope it is clear. Is there any question? No question. I hope you are listening to me, and I hope whatever I'm discussing is useful to you. Okay. You can give any comment, or you can say anything, if you want to change the way I'm explaining or something, then you can definitely comment. Next, few topics. There are, I think, two lecture videos. Those were lab classes, so I'll not go details into this. Okay, those are self-explanatory. I hope that you have watched the videos. So, in this week 3, impedance analyzer and biosafety hoods. These were discussed. Actually, those were introduced to you. Now you I hope that you already know how an impedance analyzer works from the videos, and what is the biosafety hoods, what are different classes of biosafety hoods, and on what purposes these are used. Okay, so I have taken this image from Google, different classes of biosafety hoods. You can see that in case of class 3, there is this gloves where so you can put your hands here, and you can work inside this station, so that there is no contamination from uh, the like whatever chemicals and whatever biosamples you have inside this chamber. There is no contamination, and you are also not affected from those biological samples. Okay, so this is class 1, 2 and 3. Now I will take a pause. I will go to the questions next, if there is no doubt. Okay. I hope that you are actually listening to me, and I hope that I am explaining things so that like in a way that you can understand, and the session is useful to you. Okay. When there is no response or nothing, then it's very difficult for me to uh, just speak and stay in the presentation mode and explain, because if you don't respond, then I don't know, like I'm just speaking to the screen or something. I feel like that. Okay, so if you want, then you can comment or leave something in the chat box. Okay, if there is no doubt or no comment, I will start the questions. I'll start with a very general question. You can, I hope that I will get answers from you. Okay, so this is not an MCQ type question. I'll just ask you a question, like those are discussed in the lab classes, in the lecture videos. Okay, so the question is, what are some clean room protocols? Okay, uh, like anything that comes into your mind. There are many. Okay, maybe you can recall few and write in the chat box. What are some clean room protocols? I will wait for a couple of minutes so that you can write. I'm writing the question here also. So what is a clean room? A clean room is like a controlled environment where you perform your experiments, and there are several classes of clean room based on what type of what is the number of particles present inside the clean room. Ideally we don't want any contamination, so we want a very good like a clean room, but many times maintaining a clean room is very difficult, or establishing a clean room is very difficult. uh, but I don't know how many of you have seen a clean room. There are images and videos that you can search, like, and in the lecture, in the lab videos also a clean room was shown. So, and different clean room protocols were discussed, so you can write few of those. Okay. No response? At least you can write few. Wearing clean room suit, gloves, mask and hair cover to prevent skin cell and hair from contaminating the environment. Yes. This is like the first protocol you have to follow even before entering the main experiment area. Okay. This is also to prevent contamination of the like your working space, your sample and device, as well as to this is also for your safety as well. So there will be certain chemicals, you don't want to touch it without wearing a glove. Okay. And for certain chemicals, you say from acid, we actually use different types of gloves, not the normal nitrile gloves. Okay. This is for preventing contamination, saving your device as well as to save you. There may be certain like hazardous chemicals, hazardous gases inside the like working space. So wearing proper suit and gloves and like mask, that actually is like helpful for you also. So I will write also few. This is definitely the first one. So the answer is one is use gowns, gloves that fits you, because if you use like a big gloves and then you are doing some experiment, then it is very difficult to handle like those test tubes and samples. Okay, so different sizes are available, so you want to use the one that fits you properly. Hairnet, this is again like to save your sample and to save yourself also. You don't want your hair to stuck in some machine, and if it is running, then that will create problem. Okay, face mask, so we know that our breath, so we discussed in earlier sessions also, our breath has certain like VOCs, volatile organic compounds. And suppose you are holding your sample and you are not wearing face mask, and even if we breathe close to it, there will be like acetone and other chemicals on top of your sample, so we don't want that. That is why wearing a face mask is necessary. And shoe cover. Okay, uh, another can be to maintain a particle free air quality and minimize contamination. Okay, so the filters needs to be checked. So the maintaining a clean room is very important even after establishing it, so we have to monitor it regularly, that our filters are working properly or not. What can be some other protocol? So there will be different machines, there are different equipments inside a clean room, so the maintenance of those equipments is also important. It should be cleaned regularly, calibrated regularly, uh, so that does not become bad, there is no, also no contamination from the machine itself to your sample. Okay, these are few. You can think about a few others also. Okay, they're not limited. Someone said something, or why there is a notification? Now, say you don't have a clean room, you are working in a lab which is not a clean room. So, these precautions you can also take. Uh, Wearing gloves and proper covering your hair is always a good idea, even if you are not working in a clean room. Not in a normal chemical bands also, if you are working, then it is it's a good practice. And then cleaning and maintaining your equipments is always necessary, because there may be contamination from your equipment as well. So you should maintain and clean regularly. Okay, so these are practice not limited to these protocols are not limited to clean rooms. These are for any lab, especially if you are working on sensors and you are working on fabricating, designing, and calibrating a sensor, then these are very important. Okay, especially when you talk about micro and nano sensors, something in micro and nano dimensions, because so you know a micro is 10 to the power minus 6, so 1 micrometer. If there will be one particle on top of your device, that will be of that the size will be of few microns, so your device will get damaged, your sensor will not behave properly. So this precautions needs to be followed when you work with when you are working in these dimensions. Okay, let's go to the next question. I will write down the question first. What is the primary advantage of anisotropic etching over isotropic etching? I will give you few options. A is it provides uniform etching in all direction. Option B is it is slower than isotropic etching. Option C is it offers better control over structure dimensions. And last option is it only works on metallic surfaces. Again, I will take a pause. You can write down the answer in the chat box. Okay, I will wait for some time. And this is an MCQ question, so you will be able to answer. You don't have to write like full sentence. You can just write the option which is correct. Okay. answer? Option D. Okay. So I'll give you a hint. In case of isotropic etching, the etching is same in all directions. In case of anisotropic etching, it is a directional etching. So if you are etching in vertical direction, it will mostly etch away the vertical walls, not the side walls. The etching in the side walls will be less. So now probably will be able to answer the question. Also, isotropic etching is normally for wet etching when you use chemicals. Anisotropic etching is normally when you use dry etching, when you are using ions bombardment or some like physical energy to etch away some material. Okay. Now isotropic etching, or when you are using a dry etching, like only physical energy to remove some material, that will not be very selective, right? So whatever the substrate, if the energy is high, it will be able to remove it, right? But in case of isotropic etching or wet etching, the chemicals will react to it particularly with the material that you want to etch, and that portion will only get removed. Okay. Option C. Yeah, the correct answer is option C. It offers better control over structure dimension. I have shown in the figure for isotropic etching and anisotropic etching. So this kind of profile is usually we get in case of isotropic etching. So this was your original window, you get a pattern like this. Okay, so this is isotropic. Etching in vertical as well as in side walls, this is C. Okay. Now in case of anisotropic etching, it will be usually directional. Okay. So this is anisotropic. This is usually we want, right? We are making this window and we want to etch out this dimensions. The side walls should be vertical. Normally we want vertical. Okay, there may be certain cases where we want this kind of etching, but normally we want this kind of structure. Now when you use chemical, you don't have like much control. Normally isotropic etching are chemical etching techniques where you use certain chemicals. Usually those are faster, the etching rate will be fast. Say you are etching few micrometer, say 1 micrometer in a minute, this kind of. And anisotropic etching is usually slower compared to isotropic etching, not always but usually. So this is normally slower and isotropic is normally faster. Now the second option, it is slower than isotropic etching. This can be an advantage at certain times. Say you have the option for an isotropic etching, you also have the option for an anisotropic etching of the same structure. Okay, and say you don't care much about the like the final structure, final shape of the structure. Now the etch rate for your isotropic etching is very high, say 1 micrometer per minute, and for an isotropic etching it is few nanometer in a minute, say. Now if you want to remove say few nanometer actually, then if you want to etch away few nanometer of your material, then if you use isotropic etching, then you have to do the etching for a very small amount of time. Now when your time window is very small, then you have less control. Say you want to do it for 10 seconds. If it is 11 seconds, then because the etch rate is very high, that will etch away like a significant portion of your material that you don't want. So if your etch rate is slow and you don't want to etch away like a very like significant portion, then slower etching is advantageous. But if you are going for bulk etching, okay, you want to etch away most portion of your substrate, then a slower etching, even though it gives a better like structural dimensions, then it will be like very time consuming. Okay, overall your cost will increase because you are taking more time. Okay, so there is this trade off. Okay, so it is a slower etching. Anisotropic etching is normally slower than isotropic etching. This is also true many times, but this is not the primary advantage. The primary advantage is that it offers like a better control of the dimensions. We If we are making an opening of a w dimension, width of w, then we can make our walls vertical so that it actually gives a width w at the bottom also, and throw out this cavity also. So this will be w, here also it will be w, this throw out this structure. Okay, that is why we go for an isotropic etching or dry etching. It only works on metallic substrate, so these are not very selective. And isotropic etching is not very selective because you are using some physical energy, where in case of isotropic etching you can make it very selective. So if you want only to remove your metal, then you can use certain chemical that only removes the metal, not the other portion. Okay, so usually that specific the selectivity term comes with chemical etching, that is mainly most of the time isotropic etching. So you should know these differences. So different types of etching can be wet etching or chemical etching and dry etching. Another classification is this isotropic and anisotropic. And these two terms which are associated with etching is selectivity, because etching is selective removal of material. Okay, which process is uh, like which process provides better selectivity? Usually wet etching provides better selectivity because you use certain chemical that will react with certain material. Okay, and another term is directionality. Okay, if you want vertical walls, then you normally go for an isotropic etching. So these are like, and another term is etch rate. Okay, usually you want very high etch rate if you are going for bulk micro machining, say. And if you are going to remove certain like few nanometers, then you will go for an isotropic etching, that where the etch rate will be slow, but you will get better control. Okay, let's go to the next question. Which material is commonly used as a sacrificial layer in surface micro machining? Option A is silicon dioxide, SiO2. B is gold. C is ZNO, zinc oxide. None of the above. Again, I will wait for some time so that you can answer. So I have already explained what surface micromachining is. Surface micromachining, we remove the material, we etch away some portion of the material on top of the substrate. Okay, we don't. We normally use it to make cantilever suspended beam for men's devices. So, what is the commonly used sacrificial layer? What is a sacrificial layer? That I have already explained. Like, this is a layer that we are going to remove later. Initially, we deposit it, we do the patterning to support the material of which we are going to make the cantilever or the suspended structure. Okay. Is there any answer? Option A. Option A. SiO2, yes. And why do you think that SiO2 is commonly used? What are the reason? What are the criteria for a sacrificial layer? What do you think? SiO2 is the correct answer. Uh, but why SiO2? See, I will write in the slide also. I'll just explain first. SiO2, so most of our sensors we make on silicon substrate. The reason is we already silicon is easily available, and there are other advantages of using silicon, and we already know the fabrication process, the photolithography and etching of different materials on top of silicon. So these are well known. So other substrates also we use PDMS or glass in case of microfluidic devices, but silicon is most commonly used. Now, the main advantage of silicon is that why silicon has become so popular in electronics industry. This is because we can easily, silicon is in abundance, and we can easily grow very good oxide layer on top of silicon. Okay, the native oxide. So there are oxidation, like a growth method of SiO2. It can be either dry oxidation or wet oxidation, and we can grow like very good quality of SiO2 if we need for devices, or if we want just for the insulation purpose, then also we can grow very thick SiO2 layer at a very faster rate using wet oxidation process very easily. Okay, so these processes are already well known. We can grow few nanometers of SiO2 layer on top of silicon substrate to a very thick layer. Okay, so this is one advantage of using SiO2 as a substrate, sacrificial layer. Now what you normally want is that you will pattern the SiO2 layer, you will pattern the sacrificial layer, and on top of it you will deposit some material. Now, as I mentioned earlier, that many of these deposition techniques can be like, sometimes you want to do the deposition at a very high temperature, or you want some processes after making the sacrificial layer that will go to a very high temperature, or there may be like a stress and strain on the sacrificial layer. So you want a layer which is stable for these processes. Okay, you know SiO2 is very stable. You can look like the properties of SiO2, what is the melting point, like what is the dielectric properties of SiO2, you can look, and it will not react with, for a good sacrificial layer, it should not react with the material that you are depositing on top of it. So many times SiO2 is the suitable material for that, and it is very stable, can go even up to a very high temperature, it will not get damaged. Okay. And another reason why, like we use SiO2, that ultimately we want to achieve with the sacrificial layer. Okay, so because the these processes of silicon and SiO2 is already well established, we know that using HF solution, hydrofluoric acid, we can easily remove SiO2 layer. Now it depends, like it should not damage the etching process and not damage the material on top of it, like material, the material that you are using to make the suspended structure. But because SiO2 is already well known, the etching process is also well known, so we usually use this as a sacrificial layer. Okay, so these are the reason why SiO2 is mainly used as a sacrificial layer. I will write it down for your reference. So the reason is, it is easy to deposit. We already know how to grow SiO2. And can be also. The criteria for selecting a sacrificial layer is that the deposition of material on top of sacrificial layer should not cause the sacrificial layer to melt, dissolve, or crack. Should not also, the etching process should not also damage the structured layer. Okay. let's go to the next question. This is again on sacrificial layer and surface micromachining. So I have already discussed, so you'll be able to answer this question. What is the main drawback of using photoresist as a sacrificial layer? Option A is it is difficult to deposit. B is it is not compatible for high temperature processes. Compatible. Option C is it is expensive for MEMS fabrication. D is all of the above. So you know that you can do the patterning using photoresist also. Say the figure that I showed you earlier. Here you can see the sacrificial layer is basically like a pattern. Okay, so this can be done. This patterning is can be done using a photoresist also, but we don't use normally in case of surface micro machining photoresist as a sacrificial layer. So what can be the reason? Do I have an answer? Option D and option B. Okay. So the correct option is option B. It is not compatible for high temperature processes. That is the most suitable answer. So it is difficult to deposit. That is not correct. You can most of the photoresist you can just spin coat it easily. Okay, it is not compatible for high temperature process. Why? Because photoresist are usually like these are polymers, okay, that cannot sustain very high temperature. uh, Usually polymers usually this does not cannot go like beyond all the processes we normally do is close to 100 degrees Celsius. I have not used photoresist at very high temperature. It will certainly get damaged, okay, at high temperature. So this is the correct answer. And it is expensive for MEMS fabrication. This option is somewhat true, but then again it is it depends on the situation. If you are making a device which is very critical, it has very critical dimension, and you are going to use it for uh, like a very specific application, then many times you don't care about the cost of it. But usually photoresist are expensive. But then again, if you are using as other kind of sacrificial layer, that also needs certain that also involves certain cost, because say you want to deposit a silicon dioxide or silicon nitride layer as a sacrificial layer, that will need certain instrumentation, certain machines. So we can grow SiO2 using sputtering, that we do in our lab. So SiO2 can be deposited, but then again this machine is also uh, expensive, right? So yes, photoresist are expensive, like few drops of photoresist are even expensive, but depends on the situation. So this is not the key drawback of photoresist as a sacrificial layer. The key drawback is that it cannot sustain high temperature processes, and that is why we go for silicon oxide, silicon nitride, those materials which are very stable, does not get dissolved or does not get damaged very easily. Okay, and yeah, seems like these two options are correct. That is why I've given this all of the above option, but this is also not correct. You can look for different like polymers, like photoresist exact composition you will not get, but you can look for like what temperature this photoresist or this polymer sustain. Okay. So to the next question. So the question is, what is the main advantage of soft lithography over photolithography? I have already explained what is soft lithography, what is photolithography, and what are the basic differences. The options are it uses high energy UV for patterning. Option B is it requires an expensive clean room environment. third option, option C, is it is cost effective. And enables flexible patterning. Last option is it cannot create nanoscale features. The options are such that you can easily able to answer this question, will be able to answer this question. I will take a pause and you can write the answer in the chat box. Option C, yes. The options are like the question is already clear. It's, so the correct answer is it is cost effective and enable flexible printing, patterning. So why it is cost effective and why it enables flexible patterning. So let's go through these options one by one. So first is it is high, it is this high energy UV for patterning. So this is for photolithography, not for soft lithography. Okay, so this is not correct. And why photolithography is expensive? This is because it uses high energy UV source, and so you need to do you need to go through multiple steps. In case of photolithography, you have to load your mask, do the alignment, and go for exposure. So that needs you need an instrument for that. You need certain kind of arrangement for this alignment and exposure, and then this UV source will also be expensive, and that will have some like self life. So after certain like after some time the source will be like the intensity will become low and you have to replace the UV source. So that is why this is expensive. The photolithography is expensive. The second option is it requires an expensive clean room environment. This is also true for photolithography, not for soft lithography. So we normally do photolithography in case of for a clean room environment. We want to like clean our substrate properly, and we the machine that is used for photolithography is generally kept inside the clean room, and you don't want any contamination in your photoresist layer, otherwise there will be like big particles in your photoresist and your exposure will not be good, your contact with the mask and the photoresist will not good, so you will not get the desired pattern if you are not careful, if you are not doing it in a clean room environment. At least there should be some maintenance of the clean room, even if it is not a very good like class 100 clean room, but you need like a clean environment to do photolithography. This also makes it expensive compared to soft lithography. Why soft lithography is cost effective and it enables flexible printing, because in case of soft lithography you just need a PDMS stamp, so that will be used directly like on your substrate, or depending on the type of lithography, soft lithography you are selecting. You don't need a special arrangement for exposure, alignment, and typically you don't need a very good clean room environment, because we are not going to use photoresist, we are not making contact like we do in case of lithography. And we can use the same stamp over and over again, and this is very fast, like it just say you dip it in your ink, you stamp it, then do the process, repeat the process over and over. So it can be used for a large scale fabrication. uh, the drawback is that it cannot create nanoscale features. So if the dimensions are very small, then the soft lithography is not very effective. Okay. Like ideally, I have already discussed what can be the problems if you want to make like a vertical cylinder kind of structure using soft lithography. During the peeling process of the stamp, the cylinders may like the shape may not remain as intact. Okay. Whereas in case of photolithography, because these are very like sophisticated processes, usually you once you optimize your process, you get like a very good structure, very good patterns on top of your substrates. Okay. So the correct answer is C. It is cost effective and enables flexible printing. So I'll write a few small paragraph here. In photolithography, high energy UV exposure is needed. And it makes it expensive. Soft lithography, on the other hand, which makes it cost effective and accessible technique. Even if we don't have a clean room, you can go for soft lithography. Once your master stamp is made using photolithography, so after that you can use it in like a normal clean lab setup also, without use without having any sophisticated instrument and clean room. It also enables patterning on curved surface, flexible substrates also. Okay. That is why it enables flexible patterning. whereas we photolithography we normally do on like rigid substrates. Mainly it is very popular for silicon lithography, okay? Lithography on silicon substrates, because this the PDM stamp itself is a flexible, so we can use for curved surfaces as well. So that is why it is a very flexible patterning technique, and we can make variety of devices, variety of designs using this lithography technique, okay? Hope this clear. Eight. So we have few minutes. Let's take a small question. Just write down it first. Which of the following, so this is like a revision of your lecture videos if you have watched, is an etchant of silicon? Okay. Options are KOH, option B is acetone, C is HF, D is ethanol. You can tell me the answer, and if you know what is the chemical reaction, because these are chemicals, these are chemical etchants, so what the chemical reaction also you can tell me, how it etches silicon basically. No answer. I'll show you the question here. This was discussed in the class, because in case of bulk micromachining, we mostly use silicon as a substrate when we etch significant portion of silicon. So you should know few etchant for silicon. KOH is so the answer is KOH, option A. Another is you can look for the other etchant of silicon, okay, how we can etch with silicon. The chemical reaction also I will give you. I am not expecting you to remember it, just giving you for your reference. H2O. So this OH minus comes from KOH. So it releases hydrogen. It's not a very good gas, okay? So we normally have to be careful with etching of any material most of the time, okay? So this KOH is for silicon. Acetone, for what material acetone can be an etchant? So you can remove most photoresist with acetone, okay? So this can be an etchant for photoresist. And what what is the HF is the etchant for what material, if you know. So this is for SiO2, right? So we normally use buffered BHF, buffered HF solution. This is to just to achieve controllability, so that we can control the concentration and the etch rate of our SiO2 etching. Ethanol, I don't know if it is an etchant for some material. You can look if you want. Okay, but these are like very common etchant. Basically, the materials that we are discussing in this course, these etchants are used for those materials. KOH for silicon, HF for SiO2, acetone for removal of photoresist. Okay, so these are chemical etchant. There will be like dry reactive ion etching and other dry etching technique also for removal, but normally this chemical etchant will give you very fast etch rate, and these are very selective. So that is why we normally, for selectivity, we use this chemical etchant. Okay, hope, I think similar questions are given in the assignments also, and I think it's, yeah, almost time. So if you have any question, you can ask, or we will stop the session here. Okay, if there is no question, then I will stop the session here. Thank you everyone for attending the session. I hope that the session was useful. Okay, see you in the next session. Okay, that will be on next Tuesday. Thank you.